All right. It's recording now.
Okay, great. Thanks for setting it up. The audio is a little complicated, but we're up and running. So thanks for coming to the fourth and fifth talk about Clifford Algebras. So this is going to be the last one where we actually are working in the pure theory of Clifford Algebras. And we're going to see an application of this pure theory, the K-theory, by the Atiyah-Bott-Shapiro construction. Very interesting thing that I always wanted more illumination about it, and that's the entire reason that I decided to give this series of talks, just so I could understand this thing and why it's necessary. So just to start with some easy terminology that makes stuff quicker to write down. A is any ring. I'm just going to let mod A be the monoid of isomorphism classes of A modules, where the monoid structure is just the direct sum of modules. And we're going to talk about real A modules. So real vector spaces that are modules over A. And then we're going to talk about, instead of the monoid, you can always, from a monoid, abelian monoid, produce an abelian group using the Grothendieck construction. So this is the Grothendieck of monoids. This is analogous to how you make K-theory out of the monoid of vector bundles. And it's also completely analogous to how you make integers out of the natural number. So this is exactly this construction we did this. And so we're going to have this abelian group of kind of virtual modules, like because it's always easier to work with an abelian group than a monoid. That's just how things are. So let's jump into it, where A is one of our Clifford algebras. So we're going to use this slightly easier notation. Mod n is going to be modules over the algebra CLN. And curly m sub n is going to be the abelian group constructed out of that. And then I've just tabulated all of this stuff. So the first row is things that we can do either by heart at this point or just by getting up to here and then remembering that this thing tensor that you can build it up by tensoring page 2. We had a 4-periodicity theorem. Our modules, so most of these are simple rings, meaning that there's only one irreducible module up to isomorphism. So for R, we're talking about real vector spaces. They're determined by their rank. We have complex vector spaces determined by their complex rank. Quaternionic vector spaces determined by their quaternionic rank. And if you have a direct sum of 2 copies of the same simple ring, then you have 2 distinct irreducible representations. One is given by projecting to the left factor of your ring and acting by that, and the other is given by projecting to the right factor of your ring and acting by that. So this n and this n correspond to projecting to the left and right factor, etc. These are all simple, so you get n as well. This is the direct sum of 2 things, so you get 2 copies of n. And I wrote down what are actual representations for these groups. One-dimensional complex or real space, one-dimensional complex, one-dimensional Quaternion. And then we have, this is a notation I'm introducing here, H plus and H minus. What this, well, actually, I'm not introducing it. So our Clifford algebras, I'll mention in a minute, in the dimensions congruent to 3 mod 4. I forgot to add numbers, sorry. Let me just put that in. In dimensions congruent to 3 mod 4, we have a splitting of our Clifford algebra. And the volume element inside of our Clifford algebra acts by +1 on one side and -1 on the other side. So our irreducible factors here are just, actually in terms of this direct sum decomposition, this is the plus omega part and this is the minus omega part. So this plus and minus are coming from the projection to the left and right factors respectively. You know, these are just matrix algebras, and so your irreducible representation is just the vector space of that dimension. Similarly, I wrote R8 plus and R8 minus for the volume parity representations of plus and minus stuff. Then if you do the Grothendieck construction, of course, every n just becomes a copy of the integers. And for convenience, I defined a number called Rn. This is the real rank of an irreducible CLN module. So I just wrote down what it is, right? So 1, 2, 4, 4. I wrote down 2 things here, but they both have the same dimension, 4. Right, 8, 8, 8, 8, 8, 16. So there's kind of a weird progression in those dimensions of these modules. And then finally, don't forget that we have an 8-periodicity theorem for Clifford algebras. You can increase the index by tensoring on CL8, which is R16, which is a simple algebra. So that's very important. Okay. Continue to recall stuff. Like I mentioned, we have the volume element, which we defined by choosing an oriented orthonormal basis of Rn, and then taking the product of all of those vectors. So we saw that there's a formula for the square. It's -1 to the power of n choose 2. And so we can show that easily this is going to be 1 if and only if n is congruent to 3 or 4 on 4. Write that down. So it squares to 1 only in those dimensions. And it also has the property that I wrote down that thing here. I should call that on that. If you take any vector, it anti-commutes when n is odd. Or anti-commutes when n is even, and it commutes when n is odd. So omega is always central when n is odd, and if it's even, you have a kind of funny commutation where alpha is this parity operator. Remember, alpha from the CLN. It's isomorphism, but when you factor means it's negative. So product of vectors, you just apply negative in each element in the product. You're only acting on things by a sign, depending on whether that thing is even or odd. So alpha fixes all even things, and it takes all odd things to minus that. Just remembering what the volume element is, right? So moreover, when the volume element does square to 1, for any representation, we get an eigenspace decomposition of our module. So suppose n is a module over CLN, and we get a decomposition of vector spaces into the plus and minus eigenspaces of whatever our representation of omega is. So I usually probably think m plus and m minus. So for a Clifford algebra, in particular when omega is central, this becomes a decomposition of CLN modules. And if we actually take the canonical module, CLN, considered as a module over itself, this gives us a decomposition of algebra. So it's a direct sum of these two algebras, +1 and -1 eigenspace for omega. So these are different from the even and odd things. In particular, the odd elements do not form a sub-algebra. These are very special and very particular to the case where n is congruent to 3 mod 4. That's the thing that makes this dimension special, is that omega squares to 1 and it's. Okay. So, then we started talking about taking modules over CLN plus 1 and restricting to CLN. And we had in particular this even embedding. So we had even elements of CLN. This one was isomorphic to CLN, and we had an explicit isomorphism that we don't actually be very about. We have this explicit isomorphism given by multiplying by the other element CLN plus 1. So since everything here gives you an even number of things, obviously you know that when you use the algebra, and we can show that it's an isomorphism. Let's take that okay. So using this embedding one algebra into the other, you can consider the restriction map we've done before, and using all of this theory about even elements and the volume element, we came to a bunch of very interesting facts. First was when we have dimension divisible by 4, so like 8 to the 4th in the table. If you take an irreducible representation of CL4n, you restrict it down to 3 mod 4. The volume element in CL4n splits the thing up as a sum of 2 vector spaces because it squares to 1, but it's not central in degree 4n. However, under this even embedding, omega 3k plus 1 maps to omega 4k plus 3 maps to omega 4k. Under the even embedding, you can check that. And so the omega 4k plus 3 distinguishes the 2 vector space components of this irreducible representation. So this irreducible representation over something divisible by 4 splits into 2 irreducibles that are distinguished by the volume element in the degree 4k plus 3. So that's how we got 2 distinct irreducible representations of that for that. When n is congruent to 3 mod 4, so you're pulling back these 2 distinct irreducible representations. These become isomorphic representations. You can pull them back to things that are congruent to 2 mod 4. And why is that? Don't remember off the top of my head. figures because the parity operator itself takes the omega plus subspace to the omega minus subspace. And since parity operator fixes all even elements, this map is actually a CLN even module morphism. So alpha is not a module morphism of CLN module, but it is a CLN even module, or n plus one, or whatever. I'm not sure if I actually written down these correctly. I think I only this.
Okay.
Yeah. Yeah, you gotta be careful. If you think then it probably is still wrong somehow, but we're gonna move on. So then the other two cases, this is the really peculiar case when n is congruent to 1 or 2 mod 8, if we refer back to the table. So we have complex and quaternionic. You take a complex representation, pull back to the reals, where you're just going to get a direct sum of 2 real vector spaces that are the same. And then if you take a quaternionic representation, pull it back with complexes, again, you're going to get 2 copies of the same complex vector space. So this is why 1 and 2 mod 8. When you pull back in your irreducible representation, nightmare, you get 2 copies of the same irreducible representation. And then finally, the last 2 cases mod 8, your restriction pulls back irreducible to irreducible. So this is what we did up until now. Okay. So this was what happens when you pull back representations via an even inductor. So now I'm going to think about, well, okay, there's a different, more obvious method that we might want to do. Like a simple bar to do with a bunch of information. But maybe anyone who's paying attention, they can think about what is the potential obvious embedding of this Clifford algebra into this algebra without even thinking about anything at all. You come up with an embedding in this guy, you could add that. You would have to least amount of work that you possibly do.
So getting your pad one of the story.
Even less than that.
Even less.
Don't even add anything. So you have Rn embedded with a subset of Rn plus 1. So this embedding, right, this induces a map on the Clifford algebra because commutation relation from you just send every basic code. Yeah, send the basic code. So because I introduced this thing first, it seems like everything has to be really complicated. This is a really special, tricky embedding. This is kind of like really obvious stupid embedding. As you can check the commutation relation for like obviously satisfied. So you understand everything about this pullback. Well, what if you wanted to understand this pullback instead? But we want to think about modules over CLN, which don't extend to that one more generator. We don't really have a good description of that. But
So what is the generator that in CLN plus 1?
just EN plus 1. EN plus 1. Okay. Just the basic fact that it's not divided to them. So claim there's algebra isomorphism from CLN plus 1 to CLN plus 1, sending EI to EI times EN plus 1, so I less than equal to N, and it's sending EN plus 1 to itself. Here's the isomorphism. You can define it this way on Rn plus 1 into this map or into this algebra. You can define it like this and then check that it satisfies the commutation relation. And when you go through it again, you can look like that. But it happens that if you just multiply like one more thing, you do get an isomorphism like this. And this also has the property that n is congruent to what do I want? N plus 1 is congruent to 1 both. And factor of the volume element. It's fixed. Fixes the volume. So I claim that this thing exists. I wrote down a formula for it, and you can just go check that it fixes the volume element. And then I'm going to do an even bigger claim, which I am going to do an exercise. then F star going from log n plus one to log n plus one is the identity. So in the case when the algebra is simple, this is clear because there's only one irreducible representation. I thought up to isomorphism, and this pullback map modules is going to preserve the rank. So the URF has to go back to the URF. There's something tricky to check when n plus one is congruent to 3 mod 4. You have these two distinct irreducible representations, and you have to make sure that they get pulled back to themselves. And this happens precisely because F fixes the volume. So the modular action given by pulling back is just given by like apply F first. So if you apply F to volume element, get the volume element back, two irreducible representations, where omega irreducible. So this is a check and an exercise. Don't get to go through the details of the lot of time, but the upshot is what I'm trying to show is that, oh, great. And here's a good way to write it down. There is such that this and this is the important part is that if you take our two embeddings, the easy one and the tricky one, well, they obviously just differ by the application of F. So as functions from hold on. Yeah. And now that even embedding, the weird, tricky embedding from CLN to CLN plus one was given by doing the basis embedding first, and then apply our interesting automorphism, which isn't actually that interesting because it's the identity of model. What this is telling us is that beta n star is equal to beta n star as functions from modulo over n plus one to modules over n. So
Why did you consider beta as one?
because it's a more intuitive thing to want to think about.
Oh, okay.
So there are some things where like you can see it more clearly when you're thinking about does this extend to one more basis?
Yeah, yeah.
Yeah. For example, you can show that the Atiyah-Bott-Shapiro Isomorphism is a well-defined function. You want to think about it in terms of
Okay.
so yeah,
Always going into one way.
I was going into one more. Like you can chain a bunch of them together to get
Yeah,
that
like
n-dimensional.
any number. Yeah.
So it suffices to think one at a time. Okay, so that was just kind of an aside because I had to make sure that I got around to it. Okay. All right, so now let's think about. So like I said, you want to consider modules. Modules over 10. Don't fit. This is kind of a natural problem to think about, which is naturally phrased in terms of the basis embedding. But now that we just went through this whole thing, we can see that we can solve this problem in terms of the even embedding, where we actually know everything about all of these. Well, that's the model. So let's define a group that we want to think about. En going to be our group as modulo n modulo those that come from degree n plus one. Like I just said, doesn't matter if you consider the even embedding or the basis embedding, the fullback map on modules. Okay, so if you put all of this stuff into this language, we will get the whole. So we're gonna have one n plus one, one n plus one, how we get it comes mod n, so we think about it this way. And then we're going to take our quotient of n, and then we're going to give explicitly a generator. Okay. 0 mod n plus 1 is c r. So mod n plus 1, so the table we have over there. But if you'll remember that mod, yeah, so CL1 is C, so we're looking at complex vector spaces. Complex vector spaces into real vector spaces. The complex vector space restricted to the real gives us multiplication by 2. So Qn is equal to 2, your generator for Qn is given by the one-dimensional interval. So then we have the trigonometric vector spaces being restricted to being restricted to complex vector space. And like I said before, the map of monoids from n to n, but multiplication by 2. Okay, now we get something interesting, n plus n. And so, like I said, the two distinct representations in degree 3, those get pulled back to the same representation here. So this map is actually just an addition.
Wait, but can you have extent S3, I think 3 is on.
Yeah, because this is the n plus 1.
Oh, shoot, oh, sorry.
Yeah, so for everything in this table is n except for the
Except
first
for the
row.
first one, okay, yeah.
First row that you look at is 1. So in particular, the plus map is surjective. So we get a 0 over side here. 3, we have an n, and we do n plus n. Okay. And like I said earlier, when you have divisible by 4, the unique irreducible representation here splits into the sum of the irreducible representations here. So this is the diagonal. So if you consider, yeah, so you can't get it right away from mod, but if we look at m, let's m part of a plus 3 b. So we is not diagonal. So it's a fact. Z plus Z modulo the diagonal is just another copy of Z. So our Qn here is Z. For generator is we're going to take the element H plus. And in Qn, right, because we know that H plus H minus is in the image and n diagonal, H plus is actually the minus of the element H minus. So H plus is giving us like 1 in this group. H minus is giving us the minus 1. And then I can go a little bit faster because it's totally not going to really repeat that. This part doesn't repeat it. Here we get an identity function. We get an identity function. Now it's going to look more familiar. This is plus function again. I don't know why I'm including these arrows. And diagonal. And then it needs to reveal it. Okay, and so projective, surjective, surjective, and then another probably is Z, where our H is. All right. So. Okay. So we decided to just define a group modules over CLN that don't extend to CLN plus 1. And what we look at when we take the quotient, groups are fans of K theory will see, okay, I know this. So yeah, this is the Atiyah-Bott periodicity song, right? So there's some indication that the set of Qn's has something to do with K three. If I go write that down. If this looks like bot three was. In particular, these are values. So basically, the values, the homotopy groups of the stable orthogonal group. If you just read off this line, these Q, you're getting precisely the stable orthogonal group homotopy group, which we can rephrase in terms of K theory by saying that this is the same, the shift of homotopy groups, classifying state. And then this was A minus. Did I say plus here? No. Okay, so it works, kind of works, okay? Because there's a ratio. Between Q n and K and minus one, right? Minus one string. Another thing is that K minus star is gradient, right? But Qn, Q star is not. Besides, well, we have M moving over CLN, N moving over CLM. Then we have M tensor N living over CL and tensor CLM. We're not going to go to this tensor product. This is not in general another Clifford algebra. So we have to go through a lot of work, figure out these periodicity theorems, take an arbitrary n and an arbitrary m, you can't just transfer them together and get a Clifford algebra automatically. But we did have an alternate thing where we put a little hat on that O. We had a special tensor product. But so that this tensor product is a Clifford. So all regular is you go to tensor product.
Nope, I'm gonna help you.
There. So all the graded tensor product. So if we have a graded algebra. These valuables. So we had this product defined by Hope's rule. Where we have that if you have one pair A1 and so B1, we had on it, you know, algebra a little bit, and then you take A2 little to B2. We define this to be -1 to the degree of A1 times the degree of A2, and then the thing that we normally get. Yeah, and so this means that A and B are one, so B1, B2, one. So there's a Kozel rule that we use to define this. And we had a result that says that if you put CLN, then there was CLN, and this was CLN plus N. So if instead of taking tensor products of modules, we upgraded to C2 graded tensor products, then we're going to make graded ring. So I'll just write this over here so I don't have to yell across the whole group. Doing it the race next.
Do you mind if I just add, like, do you know why that grading shift is? I can't really see why that grading shift is intuitive, or is it important because it's kind of the grammar?
So the reason is because you should be thinking about Z2 graded modules instead. So the QN is defined in terms of ungraded modules. But we're gonna see that if you define some Z2 graded modules, then you actually have one kind of alignment.
Okay.
Yeah. Great question. So the thing about these Clifford algebras is that they're like inherently Z2 graded algebras. And the representation theory works normally when it's a Z2 graded concept, and then when you're just considering ungraded things, everything's very important. So if we define Z2 graded module as M star, which is an A star module such that in addition to just being a normal module, the module structure has to preserve these gradings. So if you take AI times MJ, this should be in M I plus J. And this is where I and J 0, 1. Considered as an additive group, right? Then we can define M star Z2 graded tensor product. This is again a Z2 graded module over U star will hat U star. And this is an exercise to please check. Have you done the exercise? Yeah, so showing that the Z2 graded tensor product of algebras is associative requires you to be really a little bit careful with signs and degrees. And the same argument shows that, yeah, tensoring two modules together gives you another Z2 graded module. Yeah, to show that like the action is associative, it's exactly the same argument. It's the only really tricky thing you have to do is thinking about applying one thing and then another thing. You have to be very careful with the signs and the degrees there. But it works. So we can tensor product Z2 graded modules, and then let's define mod hat A star. This is Z2 graded modules. At right, curly M hat A star. Also just the Grothendieck group, Z2 graded modules. Just taking our old notation and just upgrading everything to include Z2 gradedness. And again, we're going to have Mn is equal to words. Yeah, words. N at ELN. Yep. And we're going to have Q at N, of course, equal to M at N. And so just like you can pull back representations along homomorphisms of module algebras, you can pull back Z2 graded representations with Z2 graded modules. So we can also do eta hat, or eta star. So you can still think about Z2 graded modules over CLN, which don't extend to Z2 graded modules over Mn plus 1.
Just from my understanding, when you say like callback representations, you mean like through decomposition, or what do you mean by pulling back?
Yeah, I might as well actually make this explicit because I'm not sure if I ever wrote down what I mean by that.
Right. Yeah.
Yeah, it just means like, yeah, precomposition. So just in design. So if M is in A mod A, we have a homomorphism from A to B. Homomorphism then, so it's a module over B, then phi star of M is a module over A via, so we're great. So what am I going to say? Your element A is acting on element M by letting phi of A So as an A module by letting it act as phi of A on M as the original B module.
Okay.
Yeah. Just to make sure that they're all. Yeah, so when I was talking on and on about the F fixing the volume element, now that preserves the volume parity, it's just because like we end up with an F of omega there.
Okay,
So it
yeah.
would just be omega again. Yeah. So
Well,
that,
omega, okay, yeah.
so if you have something with a +1 eigenvector in the original representation, then if you pull back along F, it would still be a +1 eigenvector. Yeah. So once we have this, this means that M hat star and Q hat star are graded rings. So we've come up with graded rings to fill our need for having a graded ring. But we've kind of done something different, right? We started with just modules and then we understood everything about modules. And then we suddenly decided that we want to think about Z2 graded modules all of a sudden. Have we done something completely new? The answer is surprisingly no, we haven't. Yeah, we haven't done anything particularly new. So this is good. So A star Z2 graded algebra. So then there is additive equivalence additive. So I'm gonna say R A hat. These are Z2 graded modules over A star. And the other category, I'm going to call R A 0. This is just ungraded modules over M0. So you have a graded algebra and you want to think about Z2 graded modules over that algebra, it's actually sufficient to only think about ungraded modules over the easy part. And that's actually what we were doing with the Clifford algebras already. We have every knowledge of the things you're doing over the even part. And then we can just, via whatever this equivalence is, upgrade that to a Z2 graded module. So I'll tell you how this works. The one direction is very simple. Starting with a Z2 graded module, M. So if you look back at that definition of a Z2 graded module, if you take A0, you take A0 here, then every J, MJ is going to be a submodule for A0. So M0 and M1 are both submodules for A0. And so in particular, we're going to prefer to think about the even subpart, or even submodule as a module over the even. This way, you have this thing that's a sum of A0 and A1, and you just take a 0 part. Other ways, a little trickier. So you have a module over the even part of your Z2 graded algebra. You upgrade it to a Z2 graded module by just tensoring with A over the even part. So this is a Z2 graded module. I'm saying this is a Z2 graded module. And I'm going to give this a name. I'm going to call it M hat. Giving myself writing this expression a lot. So M hat 0 is the A0. You take the even part of the algebra and plug it into this construction. So because of the way the tensor product works, this is actually an isomorphic to the original module M itself. And M hat 1 is equal to the odd part of the algebra. Tensor does a module over the even part. And I'm going to give this to you, give it a name M bar. So these are three definitions that I'm going to use later. So these are your two maps, but I'm not going to ensure for you that it's actually in categories or additive. We'll actually work as we're going to for that. Okay, so. That's great. So we have all of the stuff that we figured out for ungraded modules. It turns out to translate directly to our graded module. As long as we're promoting our module over the even set algebra to a module over the higher algebra itself. Here's a little formula that's going to help us to calculate. So let's take a pair of ungraded modules. So the even parts of two graded algebra. So there's an A star and a B star, and we can show them two arbitrary modules over them. So if we take M hat, we take the Z2 graded tensor product with N hat, then it's an isomorphic as a real vector space. You M tensor N, so N bar under N bar plus N tensor N bar like N bar tensor N. So I'm just using the distributive rule for tensor product over diagram sum. And then we start soft drawing the whole plus. What's the bar? The bar is you take the.
Oh, you find it, oh, yeah.
This is the odd part of the
Yep.
operating model. Yeah. So this is even tensor even, odd tensor odd. This whole thing is the even part. This whole thing is the odd part. So if you want to think about, so you can think about the Z2 graded tensor product, or you can think about this as kind of being the way that the product is represented on ungraded product. So this has an interpretation. Ungraded product. And if you look at it specifically for the Clifford Algebras, so here's the diagram I would draw. And had you take something over n, something over m, spits out something over n plus m. But via our isomorphisms, this thing is an n minus 1. This thing is an m minus 1. And this thing is an n plus m minus 1. So if these guys had a graded ring operation, the ring operation would land you with n plus m minus 2. But since we're actually just bootstrapping this graded ring product with degree shift, you don't actually get like an additive thing on indices, you're off by 1. But the upshot is that you do get commutativity of the diagram. You can trace pieces of isomorphism. You can multiply together two ungraded modules. And you get this. Okay. Okay. Good. Good. Okay. So if you stop setting things up, you can start figuring out what's going on. Okay. Seen a whole bunch of confusing theory. Now we get to see real vector spaces turning into complex vectors. And on example 1. Example 1. So recall we had the Q1 happened to be isomorphic to Q2 hat. We're both given by U1 so let's think about mod 1 ungraded 0. These are just real vectors. Mod 2 ungraded mod 1. Okay, so let's take the irreducible representation with the real line. Let's multiply it with itself. Here now. So formula tells us that we should take R hat, O hat, R hat, and then take the even part. And we saw that this was given by R tensor phi plus R divided by. But what is R dot in this case? That is- Okay. So. We so our bar is L1 odd until we go to L1 even. Where these things explicitly, this thing is the real span, or in P1, which is that P1, tensor over the real line, and the real span is number 1 on. So this is just the real span of our basis vector P1, but our basis vector P1, when we identify CL1 with C, this corresponds to the I of R. So this has a subset of CL1, it's identified with I R as a subset of some. Yeah. So this is R bar is actually I bar. Where it's living, this is actually living inside of the beach. So this is the even part of H considered as a module over itself. And so the odd, you know, so in fact, when you trace through all of the isomorphisms, and work this out of the notes, and we'll post the note at some point. This state IR tensor IR actually corresponds to A times R inside of the H. So the even subalgebra of H is just the span of one in A. This is isomorphic to the complex numbers. And so what we just figured out is if we took the generator in this group, we squared it, then we get the non-zero in this group. So what we figured out if you unwrap this is that P1 hat you take tensor product of R hat, you get the Q2 hat. So the way that I actually did it, right, when I looked at Q0, I looked at Q1, that would be these are isomorphic by simply hats, and I figured out that down here R just gets mapped to C. So that's an isomorphism between these two here. And I avoided thinking really hard about Q2 group simply thought of Q2. So like the first computed thing. This is the first part of the ring structure that we computed so far. This ring of representation. Found that the non-zero thing would be 1, squares to the non-zero thing would be 2. Let's go a little more complicated something. So now let's consider so consider it in degree 4. So we're thinking the Clifford algebra in degree 4, and we're looking at ZQ graded modules. So remember that this was each ungraded module for the CL3. So the CL3 was isomorphic to H filter. So this is non-white isomorphic to E up until 10, and then generated by this one is H plus and H minus. So here we're going to get H plus hats. So these are the two generators for just non-white. And we also want to consider failing degree 8. And I'll write down the analogous comment. This is failing degree 7, but ungraded, where CL7 was R8 plus 8. Then we can be a table now. So this is a potential N, and it's generated by R8 plus half and R8 plus. So we're going to make my life easier and tell these things and plug it in. Okay. Now, take mu, replace plus, and reach plus. You work it out, you get the same thing that I read, you found one. So if I dimension count. So then dimension over R was product. So that's 4 squared plus another 4 squared. So that's 32. And this is equal to 4 times the dimension of an irreducible module over this Clifford algebra that we're in. R plus. So whatever this product is, we know it's 4 times an irreducible plus or minus, right? We know it's 4 times an irreducible module over this grid. So which one is that? So because the two modules give us plus or minus elements in our quotient group Q, you really have to know which modules you actually get. You get 4 times one of the module, or do you get 1 of each, or 2 of each, or do you get 1 of one and 3 of the other? For the sake of maybe time and for people's interest, I might just policy really fast. Can't say it fast. So which 4, and again, we have to think about the actually the volume numbers. Rated tensor five. So just like the congruence of 3 mod 4 volume element distinguishes between ungraded modules in that degree, you can mention divisible by 4 volume element distinguishes between graded modules, because the volume element in the 1 degree lower maps under the even bending to this volume element. So to figure out which module these are, you just need to figure out what is the action of the volume element on all of them. And so under the isomorphism, CL4 comes to CL4, CL8. You have the W4, W4 goes to W8. And so, yeah. So in other words, the action of W8, P on the Q. In the Z2 grade, it's time to W4 acting on P. Tensor W4 acting on Q. And since these are both the plus modules, you will P number. When any elementary tensor, W8 acts by 1. So therefore, it's 4 times the positive parity representation. So similarly,
Does this work for all? Can you always just consider the action of omega on the like Q hat tensor Q hat or like A hat tensor A hat to determine, because I mean this will inevitably pop up again, no?
yeah,
Like this sort of problem.
just in that case where, remember, like it was specifically the case where we had n equal to 3 mod 4. That's the one where you actually had a different one.
Yeah,
And
yeah,
then
you're right.
you have 2 different ones.
Okay.
And then we moved it up by 1 degree to Z2 rating. So if we're things that we can by 4, now your omega is distinguished from Z2 rating modules just by adding 4 times. So you get 4 times this. Similarly, if you have omega acting by minus in both factors, those 2 minuses are going to cancel out. And so this product is also for the plus 1. But on the other hand, if you take the plus and the minus, then now you're just going to get a cumulative minus of the omega factor. And so you do plus times minus, and you get the minus. So the plus and the minus module, the real acting like plus and minus 1 degree ring, and so indeed, what we get at the end of the day is if you start in Q4, Then you take the map with the tensor product, your H. H hat, say plus minus, either one, up to Q8. And if we take these isomorphisms that we figured out in T, by choosing the generator, the positive one to be the generator, then this is multiplication by plus or minus 4. And then you get a plus here or a minus. So just to be like, this isn't saying as much because one is just the minus of the other.
Also, is when you write 4 times R8, is that the tensor product the graded one or the like?
This is direct.
This is direct sum. Oh,
This is direct.
okay.
Because
Right. The
this is
dimension
4
count
times
needs to be full.
This is a good calculation that I figured out for the first time this past week. This is always like, oh, you can go and do it. You think already. Yeah, I bet. Think for like a while about it. You can do it. Okay. And now, yes, I'll be a little bit more brief about the last example, even though it's kind of the most important one, but it's kind of also the least amount of thinking at this point. For the last example. So if you think about UN tensor with RH plus UN plus 1, this is an isomorphism. So, and sorry, not n plus 1, sorry, n plus 8. So this is an isomorphism. Moreover, n is congruent to 0, 1, 4. So this sends 1 to 1. For your favorite chosen. I mean, yeah. I'm suppressing a lot here because, you know, what you're ultimately doing is you're taking your CLN plus 8, you're splitting it up as a CLN tensor, ungraded tensor with CL8. And the CL8, and because this is a simple algebra, so any irreducible module over this, if you tensor it with this, it's going to be an irreducible module as well. So in the case where your Q is 1 or 2, or Z, sorry, in the case where your Qn is Z mod 2, then you get an isomorphism automatically. But in the case where your Qn is Z, you need to think about whether the positive module maps to the positive module or not, the omega positive module. So I can upgrade this sentence actually. Then this reserves. I'm going to say omega parity. At this point, if we even know what we mean by that. So something where omega acts by plus 1, tensoring with the irreducible module over this is going to convert that. So this is periodicity on the level of Q's. So again, I'm not going to spend a lot of time talking about that because we're out of time. Okay, so therefore, yeah, I can put this here. Therefore, what we've proven, put it on a new board because it's important. And down in there. Theorem. As Brady brings. You have Q hat star isomorphic to. We'll start by adjoining 3 polynomial variables to the integers, where the degree of xi is equal to I. You take the quotient by the relations that x1 is 2 torsion, x1 huge is 0, and x4 squared is 4 times x. So three different relator thingies, take the 2-sided ideal generated by those elements, and you get this isomorphism. In other words, you have these 3 generators. One of them is 2 torsion, square is not zero, but its cube is zero. So just to remind everybody, right? Let's see what this was, remember? So n 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, so what do we have in degree 0? We had 0, and then we had an x1, and we had it, so we had an r hat, and then we had an r hat into hat squared, and then we had a 0, and then we had a h plus hat, and then 0, 0, 0, and then r plus hat. And then here is going to be r hat tensored with whatever we r hat in this problem. So my notation is not great, but you get what I mean. So this is the group structure. So this is the thing corresponding to x1. This is the thing corresponding to x4, and this is the thing corresponding to x3. And you can see that when you continue on to the right, you just get the elements here, the representatives, but now you're just tensored with this integrated module. Okay. So what? We did a whole bunch of work in pure algebra, 100% algebra. We barely even mentioned topological spaces. And we already gave theory once or twice. Oh, that's not really good. Yes. So, the theorem by Bott is that integrated ring. So if we consider KO minus star, so this is KO of a point, which is really KO reduced 0 of S star. And this is the homotopy groups classifying space to be stable or orthogonal. So on this side, it's a graded ring because this space is like a unity ring or something. There's maps from BO to itself. This representing direct sum and tensor product of the stable isomorphism classes of ring, vector bundle over here. And so that's why this is a graded ring, but it's the same graded ring as this. So as graded rings, so a lot is generated by elements E1, I'm going to call gamma R minus R. E4 is gamma H. E8 is gamma O, where gamma little k is the tautological bundle over what? So as soon as you say
I know, I was looking at this, sorry, I got it, but it's recording, you know what?
I hope the audio is fine, but yeah. So as a graded ring, there's also these sets of generators for the reduced K theory. To make it reduced, you have to make the rank to be 0. So this is rank 1 minus a rank 1 thing, rank 4 minus rank 4, rank 8 minus rank 8. So these are the tautological bundles over the appropriate vector plane with the relations exactly given by Bott. So Q beta 1 0, beta 1 cube is 0, and beta 4 squared is 4. So doing the pure algebra, you found a graded ring structure on these groups of modules, which are remarkably exactly the same as the graded ring of stable isomorphism classical bundles over spheres. So coincidence? Atiyah-Bott-Shapiro say no. Maybe it's a little mistake. Please say no. I actually, for the first time, went and looked at Atiyah-Bott-Shapiro's paper. So Bott and Shapiro worked out these ideas for the first in a course way, and then I guess Algebra-Bott-Shapiro died. And then Bott and Attiyah worked together and did a revised version of the paper. And that's the version which is currently published. So I guess Shapiro didn't actually do anything with the writing of that paper, but he did work out a lot of the basic ideas that they expounded. A little bit sad, but it happened. Oh God. All right, let's go. Remember K theory? So we talked about K theory last time. We will very briefly recall the important bits. So X A compact Hausdorff space. Okay. So K of X is the O of X 0 is the Gollinger group. Real vector bundle. So I need formal differences. V W also virtual bundle. Okay, and we normally define. So they form, so the K groups form the cohomology theory, but we normally define the relative K groups in terms of the motion on slide A. So it's a topological thing. You have a pair of spaces and you want to define the function on the pair of spaces. What you do is just construct a space out of this pair and then define your definition using space. But we want a more Grothendieck type definition for this. Grothendieck type definition. What I can tell, the following idea is due to Rudy. He was one of the really big developers of K theory, and once people made the definition for everything, we need help to turn it into a really serious view. So here, let's define find the group L in terms of data given by following. We take an E0 to N, sigma 1, sigma N, so that's EI, the real vector bundle of that. Sigma I is the bundle morphism from EI restricted to A. If you have one restricted to A. But if you get an exact sequence, bundles, then we restrict to A, we apply the little sigma. This should be. A. And then if you consider these things modulo some relation. Now it's not the time to go into exactly what these relations are, but we're modeling, it's possible to model your figures on these exact complexes. Well, we'll call this K for now, we don't know that it's K. In fact, any complex is equivalent modulo these relations that we're doing today. One where any you what where n equals the set of data from element E0, E1, the sigma and the isomorphism in your respective field. Okay. And then, yes. So. Then. There is an isomorphism. We'll justify the more in a minute. Right now, I just want to there is one, we can do one from L at A from not A. Make it easier for you so that if A is an empty set, then all of this sigma condition is vacuous, right? If you restrict the empty set, you just get a bunch of empty functions. But if A is the empty set, then you're going to have E0 up to En and a bunch of empty functions. This maps to just the alternating sum. So this would be so Attiyah calls this type of thing Euler characteristic. So the way that they go about doing this, establishing this isomorphism with Atiyah-Bott-Shapiro, is they say that any function from here to here, which satisfies this, then the emphasis is called an Euler characteristic. I'm going to go write it down because you ever want to look into this, or this is what you're looking for. So they show that if you have two Euler characteristics, then they must be equal, and then show that if you have an Euler characteristic, and it actually uses an isomorphism for all pairs, not just for A and empty, and then they show that there is an Euler. They actually produce a construction that does this, when A is empty. And we're going to mention that, and we actually want to get our hand on some of the images of the construction when we look at them. And we might not have time for that. That's how it is. Here comes on the worst board possible right this time. You feel about to do open shop. So the introduction of these algebras was just to say that, okay, if we want to construct what we call the K theory, we can always construct one of these very strange complexes. In particular, we can construct one with just two things where a map is actually just an isomorphism on the input. So we're going through the review. Let M star means integrated module. You'll see now N. N is non-negative. Consider the disk. The unit disk sitting in Rn, and this is the degree 1 element of our Clifford Algebras C1. So in particular, our disk, any element in the disk, right, is symmetric, is able to act on M. Is a representation. So consider the disk cross M0. We're going to make a function to the disk cross M1, and we'll call it a state line. We're going to take a point X in the disk, the vector V in our module, and we're going to make this a bundle map, and we'll fix X, and then we're just going to have our X act on the algebra of our module. And since X is sitting in the even, sorry, X is sitting here with degree 1 element, so it's an odd thing. So if you act on the even element, you'll get an odd element. Right? So this is why we go from degree 1 to acting with X. So note, so X is not 0 implies that X is invertible. Precisely because we have a positive definite quadratic form. So the inverse is always equal to -1 over 2x. X. So since the quadratic form is invertible, this is non-zero for every non-zero. So away from 0, our sigma is invertible. So therefore, we get an element En cross M0 En plus M1. And then sigma restricted to the unit sphere. And then only the L and S and minus one. Which I'm claiming we have an isomorphism with A theory already. Which A O not B and has something minus one, which will go this way because we made a space over there. Reduce A theory of the N sphere, so the N sphere quotient of this space for that one. And by the suspension isomorphism, we want another kind of thing. This is just KO minus N. Right, so here is our Atiyah-Bott-Shapiro construction. And we must open the corner. So we have an ABS that goes from M and hat to KO minus N. And in fact, yeah, I don't have enough time to just like this. It's actually descending well to the quotient UF. So we get a quotient for Q and F. Well, the statement of the Atiyah-Bott-Shapiro isomorphism theorem is that ABS is a graded ring isomorphism. So theorem A to S, 1 to Q, now star, to KO, and star, the graded ring isomorphism. So what's left to be able to prove this? One is to show that it's multiplicative. This is given the time we have left. So ABS, so this is actually hard. And we need a theory of Tom classes for KO. No, we're not going to do it. No, Tom classes. So we're not going to do that today. But the other one is to show that, show that ABS of xi equals beta. So that's a lot more easy to accomplish with the technology that we have at disposal. Yeah, I did talk about Tom classes briefly in my characteristic classes seminar, but that was only in the context of ordinary covalent algebra. So let's think about a little harder again. What do we get from algebra? So if E0, E1, sigma in our L group, let X equal label I just be X equal label I. So we can take the disjoint union of two copies of X. And glue them together along their subspace A. So A comma I gets glued to A comma 1. Yeah, I'm not taking the entire subspaces and putting them at the same point, doing closely corresponding subspace. Define the bundle over Z, we call it W equals, we'll take E1, the bundle E1, disjoint union the bundle E0, now glue together the parts over A using sigma. E0 restricted to K. It's moved to E1 restricted to A by a symbol. This is a bundle over Z. The W is in K Z, but not, this isn't the only one. We want something in the K theory of X comma A. So what is K theory of X comma A? Have anything to do with the K theory of Z? Then we whip out some algebraic topology. Would be any work for us. So notice the excision of isomorphism. So we want K theory of X comma A just by relabeling this as the K theory of X0 comma A0. And by excision, this is for K, we should all have O's, obviously. K theory of Z comma X1. Of the excision isomorphism. So we have something in K theory of Z. What if we want it to be in K theory of Z comma X1? Well, there's an exact sequence of a pair. It goes through the K theory of Z down to the K theory of X1. So alpha in K O Z limits to its pair K O Z X1 and ultimately to this pair, if and only the restriction of alpha to X1 is 0. So our omega over here, restriction to alpha of X1 isn't necessarily 0, but we can do something really tricky. So consider the fraction pi from Z to X1. So if we draw a picture of all of this stuff happening, it's probably going to be easy to see. So here's maybe X1 A1. And here's X2 A2. And we make Z, which is like one bowl, move along its base to another bowl. Yeah. Here's our Z, two copies of X glued together along the common subspace. And this is the X0 part, which should be 0 and 1. And that's one part. So we can take this whole construction and just map this half onto the bottom half. That's what I'm going to define this plot. You just map everything in your X0 part, and you replace your 0 here with a 1. It's a well-defined function because it's compatible with A. We get a retraction Z to S. This retraction gives us a splitting of this long exact sequence of a pair. This long exact sequence of a pair splits into short exact sequences. So this is always surjective. This is always injective because we have this retraction. And then let delta be W minus the fullback of V1. Then you can just check computationally. Delta restricted to X1 is 0 in K theory. So there's a lift, a unique lift, because this is objective. Okay, K O V X1 isomorphic to K. So this is our isomorphic. So our Euler characteristic going from our L group to our KO group takes our bundle stuff, E0, E1 sigma, to whatever this freaking delta tilde is. Okay, so this is the actual isomorphism. This is the Euler characteristic difference bundle construction that Attiyah and Bott worked out in their paper. Here they were the first people to get this isomorphism. But the point now is that we want to construct actual geometric representations of these. because this was constructed as a bundle over a sphere. It wasn't just a relative payload thing. So what we can actually do, instead of thinking of our thing in here, we can isomorphically transport it over here and embed it into here. So in fact, not the W that we started with, but this delta that we get in this KO of Z, that's a suitable geometric representation for whatever our relative element there in KO of A. So because KO of A dead in KO of Z, we can think about image instead. So maybe one is in where you would love to use right now. Okay. So let's let our Z2 graded module that we're getting ready to plug into the Atiyah-Bott-Shapiro construction. Let's just take R hat in our Z2 graded module of CL1. So the Atiyah-Bott-Shapiro of R hat is an element of L theory. We write it like this: E1 cross R, E1 cross R, and then we have a sigma restricted to S0, maybe L of S, sorry, E1 plus 1, where sigma on the unit sphere plus or minus 1 acting on the element R, which is going to be that same element plus or minus 1. So then you get a plus or minus I on. So remember that the even part code, right, is R bar. R and R bar. So R bar was IR. So this is our isomorphism. At plus 1, you just get the basically the identity map, and at minus 1, you get minus the identity map. So when we form our Z, E1 union E1 over S0, identified with S0, right? Equal 4, welcome to the circle. Our W that we construct okay. We're just getting line bundles over each half of the circle. At one of the intersection points, we're not flipping them, and at the other intersection point, we are. So this is the tautological line bundle over the circle, aka our community. So our W that we constructed along the way to realizing the Atiyah-Bott-Shapiro construction is our tautological line bundle. But then to actually get it, we have to subtract that off the pullback of V1. But the two things that we're doing together to make our Z, they're both contracted, right? Our modules over each part that we started with are trivial. So our retraction in pi, we're just pulling back a trivial bundle from the entire. So then therefore a delta is equal to W minus pi star and R bar, which is just a trivial bundle. And so this is equal to W star. K, which lifts all the way to something K O K. 1 0. We can reduce the degree by masculine K. And so this one is equal to A. So therefore, the Atiyah-Bott-Shapiro construction. It's going to apply to X1 makes zero. So therefore, calculate so a little bit more. You take Q1 to place O minus 1, which is the next one. So this is the first example. We only have 2 more examples to go, but this is the idea. Your Clifford, this is the thing. So the other example is even better. So for N star equals C hat. We want at CL2. Then our sigma that we get when we're doing our Atiyah-Bott-Shapiro construction, at point Z in the unit circle, and we're acting on element B in a one-dimensional complex vector space, image of Z acting on B, which is exactly what we saw. This is the clutching function. For the tautological complex line. So in our Bott periodicity statement, in our goal, our description of the right-hand side of the Atiyah-Bott-Shapiro, complex one never showed up. We only have real tonionic, not tonionic. That's because for our Atiyah-Bott-Shapiro construction, this thing is actually just the limit of the square of that function. This thing is actually B1 squared. Interesting, but yeah. So these examples are great because they show you that in fact these clutching constructions that you have to just hang up off the top of your head, essentially, give up off the top of your head, motivated by the projective space construction. But the Clifford algebra formalism tells you the clutching one right there, spits it out. So much like a lot of the stuff that we saw with Clifford algebras, not only is it very computable, sometimes there's kind of, once you've set everything up enough, the computations just run themselves. You stumble across function functions. You stumble across representations that you didn't really know existed. New generating sets for matrix algebra. Okay. Because I'm totally out of time. We're a little late setting up the stuff. I will stop there, and that's also the end of my notes. Okay, thank you for coming out. Thank you for recording so many talks. So I don't know, are there questions from the audience or from chat? Is anyone in chat? No. Too bad. For complex projections, it's a two-sphere. Yeah. So you take like you take two complex planes and you like move them together like a stereographic projection. If you see that in together, you see like the relationship. Yeah, it's like it's a good way of describing it for you. So for real projective spaces, for like R N, you would take the unit here. Below the action of Z02. So the action of Z02, this is the group of units in. This is the group of units in the scale, whereas CPN is the unit sphere in complex space of dimension n+1, so real dimension 2n+2, so the unit sphere is back in dimension 2n+1. We're modding out by unit scale, which is the unit circle. So it's a little harder to just write down directly geometric construction of work, because in the case of the sphere, when you're modding it by Z mod 2, you can sort of imagine that the open hemisphere on the bottom is already accounted for by the top hemisphere, and you're just like connecting together points on the equator in equal length. So you can construct it out of a ball where you identify the opposite points. And so this is why, so in RP1, you just get a one-dimensional disk where you're gluing together the endpoints. But for CP1, it's a little more subtle when you actually go with two-speed. So you end up having like S1 is the Hawk fragment. So the reason you can see it's the two-sphere is because probably done the homogeneous coordinates for the vector space. Okay, yeah, so the point is sort of that for RPN, you can cover it with n charts, where in each chart it's like, yeah, let's see. No, a better way of saying this, so hard to describe off the top of your head. Hard to see why you do the here. But, yeah, so you can cover with charts. You want to instead of all modular subordinates, where V1 is non-zero. V2 is also the set of all modular subordinates with V2 is non-zero. And so you can normalize the set of all one is two, because yeah, so the idea is that you're taking all pairs, and we're saying two pairs are equivalent if they differ by a non-zero scale. And so if this one's not zero for all elements in the set, you can just divide through and make yeah. You can normalize all of them at once. If all of their G1 are non-zero, you can just divide through by all of their G1. You get this normalized chart. If this is going to be the set of all things, and we're going to P1, 1. And so as spaceless, this is homomorphic to the complex plane. You can Z2 from the end. This is also homomorphic to the complex. So what this gives you is two charts for CP1. And then you look at the transition function, and it's like D goes to going over the. I think that's like the transition function D goes to 1 over Z or something like that. And you can compare to the stereographic projection that you get for S2, find out that in fact, so compare it to stereographic projection, it gets you complete. Do your words so you can look it up. You get actually CP1 and DIPY and open. We will write down the same recipient charts, get the same chart. Right? Yeah, so the point is that you have the two spheres. Stereographic projection that one of your charts is listing the south pole and the other chart is listing the north pole. So in this picture, it's like one of the poles is the thing where this coordinate is 0. The other pole is the thing where this coordinate. So these two charts are exactly just like the two standard charts of the two. I don't know if that helps. The set of ones possibly the origin of the fire yeah, basically, yeah, these are. So instead of taking Sn plus 1, I could take an all non-zero vector. And this could be an all non-zero value. Or like I've skipped a step from normalized again. Okay, so Sn plus 1 should. This is like by reaction levels. You want to do the same as taking all non-zero elements like we're saying, and then you want all non-zero scales. So the 2 points are equivalent from the same line. So the same principle happens here. 2 points are the same point in CPN, they're on the same complex line. So this they're differing by an action of the element like a non-zero complex line. So if you normalize it, you just divide it. So maybe an easier way to see, you take all non-zero complex vector space of dimension Cn plus 1. Non-zero, and then you mod out by the action of all non-zero scaling. Okay, so 2 things that differ by a non-zero scalar, that means that they're in the same complex subspace. Right, so it is analogous to the real case. It's just an analogous scalars or complex numbers. So they have this circle factor inside. And so how this I know when you multiply it with the 1 over MCS. It's going to be they'll always be to a certain well, but a Mobius transform about we see by the complicated. Yeah, but it's not like that much more common. It's really just like real scaling and then also rotate. Yeah, so you don't have to worry about conversion in circles and stuff because when you're acting by scalars, like you don't have to take them you can bring it up. But the construction for complex projection space is just entirely how that's constructed in the 3D. These stuff is a dimension quite a lot, and figure these things out. Yeah, there's a lot of topological differences. You can see the topological differences. For example, all of these real projection spaces between the group you want to, but for all of the complex projection spaces are all. Yeah, there's lots of stuff that you can talk about in Attiyah Algebras. The main tool for talking about projection spaces is these modular coordinates. This is why you get parameterization of this, because like I said, we're just taking complex, two-dimensional complex space, non-zero vectors, modding out by complex scalars. So this actually, refers to the equivalence class. Well, the point. V1, V2. Either the complex scale match, you actually the non-zero. You want to just start zero because it's a singular. So this homogeneous coordinate is really the equivalence class at this point, modulo the unit scalar. You find your charts inside this set of all homogeneous coordinates by demanding that one of the coordinates be non-zero for all. So if you want to play around with complex or during the line projected space as well, yeah, a good place to start is playing around with homogeneous coordinates and boundary chart. Yes.
Was the fundamental group of RP1 Z mod 2 and not Z? Is it because it's like
RP1, RP1 is Z? Yeah.
right? Yeah.
So RP1 is the circle,
Okay, good. Yes.
but the all higher one is Z.
For RP1, it's homeomorphic to the S1, not Z, right?
Yeah. Fundamental. Yeah, Z mod 2 for higher degrees because we have a simply connected here, double covering your space. And then by the theory of the spaces, we got.
No, you said something connected for CPN.
Yeah, I meant for like the SN. You showed that the
Oh.
Y1 and Z12. I'm double covered by SN. I think I said contractible, but I meant to say it's
See. Okay,
cool.
cool indeed.
Done. Okay,
Yes.
so next week, guess we don't have the usual people we can't discuss who's going next. But I could go next as well.
Do you know what you wanna do?
Yeah, I would do like spinner bundles
Oh, nice.
and spin structures and actually the Atiyah-Bott-Shapiro construction as a fan. So you have a vector bundle over X
Uh-huh.
and you want to.
See?
Thanks for coming. So you have a vector bundle over X.
Yep.
And you can fiber-wise, if you choose a metric on this vector bundle,
Mm-hmm.
fiber-wise, you can replace the fibers with the Clifford Algebras.
Mm-hmm.
And you get a bundle of Clifford Algebra. And then the idea is that if you have a bundle where each fiber is a module over the Clifford algebra of that fiber. So you have two bundles now, you have the Clifford algebra bundle, you have some other bundle of module. So that over point X, this fiber is a module over this algebra. If you have something like that, then you can do the Atiyah-Bott-Shapiro family. So in the disk bundle over X, you can do this thing. And you get a map from modules over. Yeah, so for any module bundle for this Clifford algebra, you get an element in the K-theory of time space. This vector bundle that you started. So the big question is, okay, where do we get these bundles of time? Well, if your vector bundle that you started with admits a spin structure, then we have this principal spin bundle that we can just plug modules naturally construct an entire bundle of modules out of a single module. So given a vector bundle over X, which has a spin structure, then you get another Atiyah-Bott-Shapiro map from Clifford bundles to the Tom space of the bundle that we studied. This is something called the Halo orientation. So for an orientable bundle, so the normal notion of orientability for the like structure here we use the SOA. The orientation class lives in ordinary Clifford bundle. But when you're talking about, so when you go a little higher up the ladder, you go from the structure group SON to the structure group in spin N. Now the natural orientation class somehow lives in KO theory. And then if you go from spin N to string N, then the natural orientation class lives in topological Waterloo.
Interesting.
That's why physicists care in topological Waterloo.
I see.
So like Whitney's paper, where he writes down this like sigma genus. This was like after people already knew about elliptic cohomology. And they were already working on TNF and all of this stuff. And this was kind of just like, well, I mean, I don't know the history, so I shouldn't say really, but it's sort of like he knew all of this stuff was happening in the math world, and he was like, here's a like a physics manifestation. You can just write down this thing at a physics level. And then we figured this is probably like a string orientation of something.
I see.
And it turned out that yeah, it was. So yeah, it's like it ends up being a map from spin cobordism ring to the topological modular forms, something like that.
Okay, I'm gonna stop recording now.
Okay.